Science time. Today we are talking about Newton's laws. So if you could please write that down. Forces and Newton's laws. That's in pink. Forces and Newton's laws. Forces and Newton's laws. Thank you, brother. Okay, today's objective, which you should write down, I forgot to do this last time, but determine patterns of cause and effect in forces is our objective. Determine patterns of cause and effect in forces. What would be a great way to start this discussion, can you think? What would be a good thing for us to talk about first, if you were to organize this yourself? What should we talk about first? Do you know what a force is? Push or a pull. Yep, I like that. Push or a pull. Can you give me an example of a force?
Gravity.
Okay. Can you give me an example of the force of gravity acting on an object? You mean that gravity would push it down? Yeah, okay. Give me a specific example. I bet you can think of one. I bet you can hear one.
Rain.
The rain. Yeah, it's raining outside, which is really, really quite rare. I mean, of the weather phenomenon that we experience in this part of the world, rain is probably the rarest. It's really interesting that it's happening. But gravity is part of the reason, part of the cause and effect of that rain, right? Patterns, it says, of cause and effect. So we have pushes or pulls. Give me some more examples. You have gravity. What other kinds of forces are there, generally or specifically? And by that I mean you could provide a kind of force like gravity or a specific instance like rain being pulled down the planet Earth, right? So either specific or general. Give me some more examples of forces, of pushes or pulls acting on objects.
I don't know if this would but Earth's gravitational pull.
Yeah, we got gravity. So you can make it more specific by saying Earth's gravity, sure. Net force, okay, let's put that one. Let's put that over here. Net force, what else? Balance forces. These are from your vocab, I'm intuiting now. Balance forces. And we are going to keep both of these up there because we need to talk about both of those in quite a little bit more detail. But give me some other examples of, do any of you have siblings?
Yeah.
Yep. Does anyone not have a sibling? No only children in this room. Raise your hand if you or your sibling has either been pushed or pulled by you or your sibling. Everyone but Suri. Suri has never, under any circumstances, been pushed or pulled by either Camilla or Abby. She has pushed. Raise your hand if you have pushed your sibling down the stairs. God bless you, Kyson. Okay, okay, now also raise your hand if you have been pushed down the stairs by your sibling. So that's kind of a combo force because we have a push caused by your sibling and a pull by gravity. So when we think of just push and pull in the normal, maybe physical or almost social context, we can think of that like I'm going to put a social push. Like if you're about to get in a bar fight and you get pushed by a guy, that kind of push is also a force. What other kinds of forces are there? Okay. I mean, that's kind of all of this, right? Good. I'm going to put it, though. What else? Give me some more examples. You can probably think of other ways the forces act. I want at least a couple more. Okay, good. I like that one. Snow's fine. I mean, it's right along with rain. We could put precipitation of the weather. Yes, give me a second, though. Precipitation of the weather. I almost said no, but of course that's not true. It's just that gravity doesn't cause it. But yeah, the wind can definitely provide a force. Can you think of an example of the wind providing a force to an object?
Pushing a tree over.
Yeah, pushing what did you say? Tree? Yeah. She said twee, but that's okay. It's just your accent. Here's one way that I think about the wind as a force a lot is that I have no reason to be interested in this because I live in the middle of, like, as far from the ocean as you possibly can live. But I really am interested in and attracted to sailboats. I have a little model sailboat above my bulletin board over there. Do you see it? And the force of the wind is what propels a sailboat, right? It's harnessing the power of the wind. And so there's definitely a force that is the wind. Someone else said downforce. Actually, that's not at all dissimilar to the forces that act on You mean downforce in the context of racing cars, I assume.
Yeah.
So like the spoiler of a racing car provides downforce so that even as it goes faster and the car almost lifts off the ground like an airplane might, the spoiler keeps it on the ground by providing downforce for the racing car. And that's definitely true. And it works actually almost in the same way as the wind works on sails when they're rigged in a certain way, and that is as a wing. So both of these things are kind of like wings that cause forces to act in certain directions, which is a really, to me, as I say again, both of those are really fascinating applications of the force of the wind. So here we have several examples of forces. All of them are pushes or pulls, and all of them work within the confines of net force and balanced force. So those are the things we're going to talk about. In fact, since we already have them up there, let's talk about those first. But one last thing, one other thing that maybe you forget about as a force is this idea of what we call weight. You know what weight is. You have a weight. You might lift weights. You've used the word weight before. Weight means like what? How what something is. Give it to me like you would give. Oh, very, very close. I'm surprised you said that. How what something is. Yeah, how heavy something is. So this has a weight, right? This has a weight, not very much weight. Look at how I can do it. Woo! I could do a similar thing with this. I'm going to knock everything off here. That's a little bit heavier. But weight is actually the force of gravity on an object. Force of gravity. I really need to lock in with my penmanship. I'm sorry. Force of gravity on an object. I really can do a better job. I have just neglected to do it. The force of gravity on an object is called its weight, and it's not its mass. It is not the same thing as, have you ever seen this sign before in mathematics? What does that sign mean? Not equal to. It is not the same thing as mass, but it is related to mass. That means to say that weight and mass are not the same thing. 8th graders, are weight and mass the same thing?
No.
No, they are not the same thing. But the more mass an object has, the more gravity acts on it, and so the more weight it has. So they are related, but they are not the same thing. And this is tricky because in the SI we use units of kilograms for mass, but confusingly we also use those as units of weight in the SI sometimes. That's not technically the way we should do it, but we can convert, at least on Earth's surface, we can convert from pounds to kilograms. Like you might know your weight in pounds, but you might be aware that at the hospital they record your weight in kilograms. And so something's a little bit amiss there where kilograms are a unit of mass, pounds are a unit of weight, and I'll tell you the only reason that works is because on Earth's surface the force of gravity is the same. We'll talk about that in a second. But weight and mass are not the same thing, but the more mass something has, the more weight it has. Weight is defined as the force of gravity on an object, and mass is defined as how, lock in, how much matter is in an object. It's just a measure of how much matter there is. Do you see the difference between those things? An object floating around in interstellar space would have mass. It has a certain amount of matter in it, but the force of gravity acting on it is negligible, so it might be weightless. All right, you've heard the word weightless before. So it might have very little gravity acting on it. Now, when we talk about net force and balance force, you remember from, I think it was you guys, the last video we did, we talked a little bit about this, where was it you guys that drew a picture of you sitting in a chair? Joe Dirt. Oh yeah, with the car. Let's do that again. Let's draw, because it was going to be your mom, but that's a little bit offensive. So let's draw Joe Dirt again, because like your mom, he does have a mullet. Okay, so here we've got Joe Dirt in his car with his mullet. Joe Dirt in his car with his mullet. Oh, I want to put this in picture. Have you guys ever heard the word mullet before? It's like when someone has hair, long hair in the back. If I could have a mullet, like if I could snap my fingers and have a mullet, I would. But it takes a lot of constant conviction. You have to convince yourself every single day that I still want this mullet.
Just cut Joseph's hair off
No.
Who's Joseph?
Joseph.
Oh yeah, no. I won't. Anyway, so this is Joe Dirt, and let's think about the forces acting on Joe Dirt. Let's say he's in the Kmart parking lot. What forces are acting here on Joe Dirt at the Kmart? Remember, first of all, let's rewind our minds to the last discussion we had. Is he accelerating? If he's sitting still in Kmart parking lot, is he accelerating? No, not accelerating. He's at rest. Remember, there's another way that objects cannot be accelerating, which is if they're moving in a constant line or in a straight line at a constant speed. But in this case, he's at rest. What forces are acting on him? Well, he has the force of gravity acting down on him. You're right about that. How do you know, and what would you call the force of gravity acting on him? How do you know he has the force of gravity acting on him? Okay. Evidence suggests, right, that he has the force of gravity acting on him because he's not floating off of planet Earth. What else? How else do we know he has weight? I'm sorry, I gave that one away because I was going to ask you, what do you call the force of gravity acting on him? The force of gravity acting on him is his weight, right? F sub g, which is force of gravity, which is also the same as his weight. Now, the fact that he's also not falling means that this can't be the only force acting on him, meaning that the forces must be balanced. So what is balancing the force of gravity? Okay. In a sense, yeah. Just in his body, you're right. In the context of the car is providing that balance, or the ground is providing it. But in the context of his body, the car seat is providing it. And we call that upward force. This is synonymous with you sitting in your chair, right? Are you falling? No, you're not. Your gravity is acting on you. You have weight, but you're not being pulled downward. You're not accelerating downward due to gravity because your chair is holding you up, right? And we call this force the upward force acting on an object that resists the downward force of gravity. We call that the normal force. F sub n, the normal force. This is a very normal name. The normal force. So why does Mason Maynard not fall out of his chair? Because the normal force is pushing up on him. Okay? Actually, in the strictest sense, the normal force does not counteract gravity as such. It actually works perpendicular to the surface you're on, which is why if you make the chair, if you tip the chair eventually, hey, you know, I'm trying to tip you out of your chair. If you tip this chair, eventually he will slide out because the normal force doesn't act up. The normal force acts perpendicular to a surface. So if you're sitting flat on your chair, the normal force does act up. But if you tilt the chair, the normal force starts acting this way, and now friction is what's holding you on. By the way, friction is another very important force. We should add that to our list. Friction is the force that does what? What does friction do?
Creates heat on the ground.
It does create heat. I like that. Let's put that. Creates lock in.
The resistance of surface of an object.
Resistance to what?
An object?
No, it's within an object, or it acts on an object, but
on the surface.
okay. To what? Resistance to motion. Right? Friction is that force acting between surfaces that it resists motion. What has more friction, a rough object or a smooth object, generally? A rough object has more friction. I forget now exactly what my question was. A rough object has more friction, and that's because if you look even on a smooth object microscopically, you'll see these, and what happens is that these teeth, kind of, they're not really teeth, but the roughness of the object sits in the valleys of another object touching it, and they get stuck together, and then it takes a little bit more force to move them, and that's friction, right? You can do this, and that's friction. How can we reduce friction? People love when I talk about this. The answer is if we fill this in with usually some fluid, it's lubrication is what it's called, and that reduces friction. It basically makes rough surfaces smooth by filling in the gaps. So that's one way to reduce friction. So if we really wanted Mater to slide out of his chair, we would make this seat greasy or oily or even just wet because that would reduce the friction. Because once the chair starts to tilt, the normal force goes from being up to being kind of sideways, and friction has to hold him on. Likewise, if we wanted him to stay in his chair, even though we tilted the chair, we might like glue sandpaper to the seat of his pants and also put sandpaper on the chair because that's very rough, and so they'd stay together better. So we have friction. For this diagram, back to our Joe Dirt diagram, those two forces are what? We would say, I'm going to erase this over here, the net force, which is what happens when we add all the forces together, F sub net equals what? If we add all these forces together, what do we get? Well, we have, let's say this one is positive and this one is negative. We can tell from the length of the arrows that they're about the same magnitude, right? They have the same greatness. They have the same amount. So if we add a positive and a negative of the same amount, Mr. Certainly tells me you guys are bad at this, but I'm going to trust you to tell me the answer. A positive and a negative, but they're the same amount, what do we get? Zero. So if net force equals 0, we call that a balanced force, or we call those forces acting on it balanced. Now, if the net force is not equal to 0, let's say he starts his car and he starts going this way. We got now the thrust force. We have a rightward force acting on it. Now what's the net force? Well, it's not 0, right? It's some other number. Let's say it's 2. I don't know. So if he has a net force of 2 newtons, by the way, that's the unit we use for force. Can you guess who that's related to? Newton, like Newton's laws. It's named after Sir Isaac Newton. But if we say we have a net force of 2, here's the thing, and this is going to get us right into Newton's laws. If there is a net force, there must be. This is where it all fits together with last week too. There must be acceleration. There must be acceleration. I'm actually going to write out the word acceleration instead of the symbol, and I'm going to write it really neatly. Oh my goodness, I'm doing a terrible job though. Acceleration. And this is Newton's. I need to find a better way. So how did we get net force, by the way? I'm sorry, I'm just going to make a little sidestep here. How do we get the net force?
Add all the forces.
There we go. So let's write that down. Add all forces acting on an object together. No, I'm not kidding. This is the truth. This, I'm going to do a real crazy Danny DeVito thing here. And this, what I just talked about, is Newton's second law. It's also especially crazy that I didn't even start with the first one. Newton's second law is that an unbalanced force, what else could we call an unbalanced force? Jasper, not looking out the window. What else could we call an unbalanced force? Unhinged guess. What else could we call an unbalanced force? Anyone? What's another name for an unbalanced force?
Tilted.
Net force. So any non-zero net force is an unbalanced force. So an unbalanced force causes acceleration. Hey, define acceleration for me again. We had it last week, but I hope you remember.
Speed up, slow down, and change direction.
Change. Yep, those are the 3 ways. Define it in general. Those are all changes in what?
Moving.
No. Just motion in general, yeah. An unbalanced force causes acceleration, which is a change in motion, in the same direction. So if I apply, you'll know this instinctively, but if I apply what is to me a leftward force on this stand, what's going to happen? Its motion will change left, right? I'm not going to do it too hard. Do you see? If I put an unbalanced force left on this, guess which way it moves? Left. You know that instinctively, right? If you want your sister to fall down the stairs, you push her in the direction of down the stairs, right? Right?
Yeah.
Because an unbalanced force causes acceleration in the same direction. That's the Newton's second law. There's also some math with that. I'm going to just show you the math. F equals m times a. This will be on your test. Force equals mass times acceleration. Force equals mass times acceleration. We'll work on that as we work on our review. Force equals mass times acceleration. So that's Newton's second law. What else should we talk about? We started by talking about what are your examples of forces, and we got all the way to Newton's second law. What else? What's the next thing we should talk about? Newton's first law. That seems reasonable to me. Newton's first law. In one word, it is this: inertia. You've probably heard the word inertia before. Inertia is actually the Latin word for laziness. If you're big into the 7 deadly sins, the one that people call sloth is inertia. That's the Latin word for sloth, for laziness, is inertia. And what it describes in physics is an object's tendency not to change motion. A tendency not to change its motion. So it's often phrased as an object at rest stays at rest, or an object in motion stays in motion unless acted upon by an unbalanced force. And that's inertia. So what that means is that I can reasonably expect that if I set these markers here, that their motion won't change unless something happens, right? I can safely come back Friday, and my markers will still be here unless someone in this room, or something, causes an unbalanced force, right? This marker is going to stay there unless I put an unbalanced force on it. There I am putting an unbalanced force on it. Likewise, I know that since your grandma, Mrs. Lambert, will be here tomorrow, if I come back and my markers are all moved around, they didn't do it on their own, right? Because of inertia. Something had to happen. I'm like, Mrs. Lambert, what were you up to with my markers? Similarly, if I look, check this one out. This is where people get a little bit tricked up. If I roll this ball, Newton's first law tells us that it's going to keep going in a straight line in a constant speed forever. Does it actually do that forever? No. Why? What happened? Because of friction. So in the real world, there's friction. But if I were to do that same thing in, again, interstellar space, if I just threw the ball, it would keep moving in a straight line at a constant speed forever because there's no outside force like friction to act on it. Okay, and that brings us to Newton's third law. Newton's third law, which is, I'm going to just call it force interactions. This one is often phrased as, you will have heard this one, this is probably the most famous one. For every action, there is an equal and opposite reaction. That's often what Newton's third law is phrased as. I just call it force interactions, because they're actually one thing. This is a lot of times phrased as, if you kick the soccer ball kicks you back. Like you feel it. If you were to, if I were to punch this wall like I'm an angry weirdo, the wall punches me back. And how do you know? Well, you get a little owie on your fist. I don't know if you've ever punched anything. You say you all have siblings, and so you have punched something. But when you hit something, it hits you back. You notice it. You feel it too. And that's an interaction. Whatever force happens, the same thing gets a force acted back on it of equal strength, but opposite in direction. Equal in magnitude, opposite in direction. That's a force interaction. We'll do math with that next year. So that's Newton's laws. That's the patterns of cause and effect in forces. Do you have questions about these? Your book also talks about, your study guide also talks about projectile motion. Have you heard of a projectile? A projectile is when something is moving through the air. So that means it's moving through the air in that it has a certain horizontal direction, but it also is being pulled down by gravity. That's what a projectile is. Your study guide goes into quite a little bit of depth in that. And it also talks about circular motion. Can you guess what shape circular motion does? There you go. So for now, if, like on your vocab, you can define projectile motion and circular motion, that's okay. When you're in physical science, we'll do a little bit more work with those math and concepts. But for this discussion, if you can understand and have memorized Newton's three laws, and if you understand how forces are added up to get either balanced or net forces, and what forces are in general, then you're good. Do you have questions about any of this? I thought you probably wouldn't. Bye!